Hello everyone, my name is Paridhika Kayal and I am a PhD student at University of Toronto. Today I am excited to present my recent work, DNNSplit, which is a latency and cost-efficient split point identification technique for multi-tier partitioning. So first I will be going through the motivation and problem statement and with some assumptions I'll define the problem and then I will uh, go through my strategy for split point identification. Then I'll prove the effectiveness of these points and then uh, the evaluation and conclusion. So hybrid multi-tier environments are usually utilized for DNN inference tasks. And all the previous research on partitioning DNN models involved leveraging all layers of DNNs to identify latency or cost-efficient partitioning. But due to their computational complexity, these approaches face scalability issues with DNNs containing hundreds of layers. So in case when there would be any network changes or hardware or infrastructure changes, these strategies would require to go look through all the hundreds of layers again with any change to change their partitioning decisions. So which is not feasible with the models with large number of layers. So there is a need of identification of some potential split points in these DNNs for latency and cost reductions. So the DNN partitioning problem can be posed as how to efficiently adapt the partitioning decision to minimize latency and cost without the need of to consider all layers of DNNs with numerous layers. To this, our contribution is the devising the strategy for identifying potential layers in various DNNs that can serve as effective split points for minimizing overall latency and execution costs. These split points remain independent of network conditions. So first, I will familiarize you with some assumptions of my model. So we assume that the processing capacity of the tier increases as we move to the upper tiers. So the edge is considered as least powerful and cloud is the most powerful. And the second assumption is that the processing cost is decreases as we move to the upper tiers. So which means the processing cost at edge is highest and cloud is cheapest. The third assumption is that the bandwidth is not free, which means when we transmit data from edge to near edge, we would pay something for the bandwidth for transmission cost. So, and we consider that it is not zero. So with these three assumptions, now I'll show the strategy that would help us to find the split points that are efficient in latency and cost minimization. And we will also prove, I will also prove that there are no other split points other than these which can ever cause a latency and cost improvement. So first, let's consider the processing need of entire model to be APM, which is the sum of the processing requirement of model of from layer 1 to the last layer. Now, ADL denotes the amount of input data that is required for a DNN layer for processing. Let SPM denote the set of these feasible points that we will compute now. So first, when there is no point in the set, we will just add the first layer of the DAG to of the DNN in this set. And going further, we will only add those layers for which the input data requirement is less than than any of the previous input data input data requirement of the partitioning points that are already added in the list. So these split points that we will get using this formula will not depend on any bandwidth values between the tiers, and also they will be independent of infrastructures. The only thing that is required is that they should follow these three assumptions. And in that case, these will be the only split points that can ever help you to get a latency or cost improvement. So now I'll prove why these are the only possible split points. So first we will prove this effectiveness of this selected split points for latency minimization. So let's consider the first scenario when the entire model is processed on near edge. In that case, the latency will be computed as the transmission latency of the data required by the first layer to the from edge to near edge, and then the propagation delay from edge to near edge, plus the computation time required for computing the entire model on near edge. Now consider the second scenario in which S1 minus 1 layers, initial S1 minus 1 layers are offloaded on the edge and the rest of the model is being processed on near edge. Now in this scenario, let's consider that AP S1 minus 1 denote the amount of computation that is required for the DNN from layer 1 until S1 minus 1 layer. So these layers are being computed on the edge now. So now the first term will show the computation time of these layers on edge. Now we transmit the data required for S1 minus 1 S1 layer to near edge. So this will be the transmission time for transmission of S1 data for S1 layer, and this will be the propagation delay. And the third term denotes the processing time of the remaining of the layers on near edge. So now, if we want the second scenario, that is the partitioning at S1 to be beneficial as compared to the first case, then we need that the latency in the second case should be less than the latency in first case. Otherwise, there would be no point of choosing the second case as a better choice. So, following this inequality, when we put up these terms of latency 1 and latency 2, we get the following inequality, in which we can see that this first term is positive because of our first assumption, where the processing of edge is less than the processing at near edge. And so the right hand side should also be positive in order for this equality to hold. So which gives us this inequality that the amount of data that has to be transmitted at a layer S1 has to be less than any previous data that we have already considered. So initially we have considered the layer first as our possible split point. So any next split point that we will add should have a less amount of data that needs to be transmitted to the upper tier. Then only the point will be feasible. So we prove the similar proof for the cost effectiveness of these split points. So similarly, consider the first scenario where the entire model is processed on near edge. And in that case, the cost can be computed as the transmission cost and propagation cost and the computation cost. Then the second scenario is the similar where S1 minus 1 layers are on edge. Then again, we can compute the cost in the second scenario, and similar to the previous one, in order for that partitioning S1 to be a feasible partitioning, the cost in the second scenario has to be less than the first scenario, and with which we get the following inequality. So again, with the right hand in the left hand side, the second term is positive because of our second assumption, and the cost of transmission is positive with our third assumption, and that is why the last term has also to be positive. So which gives us the same inequality that again only those layers will be feasible for which the data transmission required is less than the previous ones. So only the split points that has the amount of transmission requirement in decreasing order, in monotonically decreasing order, will be the preferred points. So now I'll show that how much improvement can be gained by using only these split points for our adaptive strategy to find the partitioning points in multi-tier environments. So the first plot shows different models on axis. And on y-axis, it shows the improvement factor, which means how much improvement will we have by considering all the layers and rather considering only the split points. So like we can see that for larger models, we can get up to 100 times improvement by looking only at these split points. And on the left, I show in the table the split points that are detected by this strategy for various models. So now I'll pose the DNN partitioning problem. So the first equation shows the latency of splitting the model into two partitions, S1 and S2, where S1 minus 1 layers are on the edge, and then the data for layer S1 is transmitted to near edge, and then the remaining the layers from S1 minus 1 to S1 to S2 minus 1 are processed on near edge, and then layer S2 is transmitted on the cloud and the remaining is processed on the cloud. So similarly, the second expression shows the cost in this particular scenario. So we denote DM and DM as the QoS and SLA requirements, and the optimal latency is defined as the minimum latency that we get for any S1 and S2. So we try to find the S1 and S2 for which we get the minimum partition latency, while the latency being within the budget, within the deadline, and cost being within the budget according to SLA. So similar problem we pose for the cost. So now I'll show the improvements that we can get by DNN-split algorithms. So on the left hand side in this plot, I compare with two different edge devices that how much improvement can we get compared to edge only execution of the DNN models. So I specifically choose lower bandwidth because in lower bandwidth scenario, the edge only solution is preferred. Here, the black line shows in the upper plot the speed up equals to 1, and the black line, dotted line in the lower plot shows the cost reduction factor equals to 1, which means there is no reduction that we have achieved. If the bar goes above, then there is some cost reduction we can achieve by using the DNN-split strategy. So for cost, I have used the cost of edge device, which is the sum of operational cost as well as the um, uh, fixed cost, which is the purchasing cost. So in both cases, we can see that there is a speed up and cost reduction factor greater than 1 achieved by splitting the model between edge, near edge. And in the second scenario, we can see that since Jetson Nano is a model with is a larger has larger capacity as an edge device, so it is able to execute full models on it itself, and without it does not prefer transmitting them to the near edge or cloud in case of lower bandwidths. So in these plots, I show the improvement compared to near edge in the left and compared to cloud in the right. So I use different bandwidths to compare with near edge and different for cloud because these are the bandwidth at which near edge only solution is the best. So I compare with them at that bandwidth with near edge only, and so on cloud. So in both these cases, it shows that DNN split is capable of achieving latency and cost improvement compared to a single tier execution. So now to conclude, DNN split identifies latency and cost efficient split points. And these split points are independent of infrastructure and bandwidth variations. And we have also proved that these are the sole candidates that can provide an advantage in terms of latency and cost. This research eliminates the need of looking at all the layers of DNN, which will enhance the complexity of algorithms of all the researchers which are aiming to find algorithms for DNN partitioning. Also, we can achieve, we found that we can achieve up to 100-fold complexity reduction by just looking at these split points instead of looking at all. Thank you. I hope you enjoyed my presentation.